I guess we should get started then. So welcome. I'm actually pleased that there's a lot of people in this room because it will raise the temperature in here somewhat. So, because I'm feeling a little chilly. So welcome to my talk on transaction management in a microservice architecture. And really what I'm going to talk about is that even though ACID transactions are great within a service, between services there are various sort of distributed data management problems. And so to maintain data consistency across services, you have to use an approach known as Sagas. So kind of like that's the transaction model for a microservice architecture. So, but before I get into that, a little bit about me, and I should say, for those of you who live in Northern Europe, don't give up hope. You will see blue sky and sunshine eventually. Though this is not where I live. This was actually in Australia back at Christmas time. Anyway, so I got my start in programming it was lifetime ago, 30-odd years, building Lisp systems, so kind of programming language implementation, compilers, runtimes, and all of that good stuff. Eventually, programmed in Java, wrote the book Pojo's in Action, which was about Spring and Hibernate. That was, 10, 12 years ago. Did a whole bunch of stuff on Amazon EC2, created the original Cloud Foundry, which was a PaaS for deploying Java applications on AWS. And that was then acquired by SpringSource and then VMware. And I was there for a while. And basically, since about 2013, I've been pretty much focused on the microservice architecture. So I do consulting and training, sort of various locations around the world. Have a startup creating a platform to simplify the development of business applications that run on the microservice architecture. And I'm hopefully close to finishing a book on microservices patterns. Which if you use this discount code, you can get 40% off. So I actually sent the final chapter off, or draft of the final chapter off to my editor about 2 weeks ago. So it's getting closer and closer to being done. And you want to know more, go to learn.microservices.io. So enough about me. Let's talk about transaction management in a microservice architecture. So first, a little background, as in what is the microservice architecture? And it's basically an architectural style that structures an application as a set of loosely coupled services. Thus each service implements a particular business function or business capability. But it's basically applying functional decomposition to your architecture so that you end up with a set of services, which are independently deployable, smallish applications. And for me, the primary reason to do this is to enable basically continuous delivery or continuous deployment, which is another way of saying DevOps, of large, complex applications. And the reason you want to do that is because the microservice architecture gives you the testability that you need to do continuous delivery and deployment. By decomposition, you have services that are easier to test. They can be tested in isolation. And it also gives you the deployability as well. You can deploy each one independently without coordination. And it also facilitates the autonomy of small, nimble teams. Each team owns one or more services. Anyway, so that's sort of the background. Then when you apply that to this example, which is a sort of an online store, you actually end up with a sort of many more moving parts. So it's sort of a more complex architecture, but that's sort of a whole other talk. But the big idea is that in order to ensure loose coupling, each service has its own private data. So that doesn't necessarily mean private database server, but it could just be a set of tables or a schema on some shared database server. But the concept is that the data is private. And the primary reason for doing this is to ensure loose coupling between services. So if I'm working on the order service, I know that I can freely change the schema of that service without having to go talk to the customer service team and the 10 other teams that are also have written services that access my schema. Because that just totally destroys autonomy, slows down your delivery velocity, and so on. So that's why there's this kind of key rule that the data for each service is private to that service. But then that creates a problem, namely how to maintain data consistency across services. And the example I like to use is, so let's imagine that customers have a credit limit. So, in other words, when you place an order, you have to verify that that order would not exceed the available credit for that customer. And that has to be enforced at all times, even if there are multiple concurrent attempts to create orders for the same customer. And in a monolithic application, that's trivial. I mean, there's subtle issues around isolation levels and so on, but you basically just use an ACID transaction where you find the existing open orders, sum up the totals, find the available credit. If there's sufficient credit, you can create a new order, and the properties of an ACID transaction will ensure that this business rule is enforced at all times. The problem you have in a microservice architecture, however, is that now orders are they belong to one service, customers belong to another service, and so you can't trivially write a transaction that accesses tables that belong to multiple services. And then even if you did, you'd have to use some form of distributed transaction in order for these services to participate in that one transaction. Obviously the classic way of doing that is to use two-phase commit or distributed transactions. That essentially works, but there's sort of a whole host of issues with using distributed transactions around, which basically impacts availability and performance, and throughput and so on. Plus many modern sort of database technologies, many NoSQL databases, for instance, don't actually support distributed transactions. So there's kind of just a whole bunch of practical reasons. And then also the CAP theorem basically says, well, you have to choose between consistency and availability. And basically the decision, the consensus is that it's much better to be available rather than consistent. So it's sort of like, this whole ACID model it doesn't apply across services anymore. And when someone coined the phrase base model for transactions, basically available, soft state, eventually consistent. So it's kind of it's kind of an interesting acronym. I don't know whether it's entirely caught on, but it's sort of saying in these modern systems, we're not going to use ACID in quite the same way. We're basically using an eventually consistent model. And that's what leads into the idea of a saga. And the term saga comes from this paper that was published back in '87, I believe. So it's quite an old idea. Strictly speaking, what I'm talking about is sort of a specific form of sagas, namely a distributed saga. The original concept was sort of more limited to a single database. But the idea with a saga is that instead of a single transaction, a distributed transaction that spans multiple services, instead you're using this saga model, which is a sequence of local transactions. So one service does something, and it actually emits an event or a message that triggers the next local transaction in some other service, and so on and so forth until all of the data that you want to update has actually been updated. So the idea is simple. Just break up your transactions into a series of local transactions. And each step of the saga, occurs in one service which updates its database. Could create an order, could reserve customer available credit for a customer, and then it's also publishing a message. And then just in terms of what gets updated, I mean, the actual kind of scope of an update within a service actually varies. So if, for instance, you're just on top of a relational database, well, you can begin a transaction, update arbitrary rows in that database, and commit the transaction. So all within the scope of that one service. If you're sort of following the strict domain-driven design model, for sort of business logic, a transaction will just update a single aggregate. And if you're, that's sort of using DDD terminology, if you're running on top of a NoSQL database, then a transaction will typically update a single record. Though some NoSQL databases have a sort of, not exactly ACID transactions, but sort of a slightly more general transaction model. So the actual scope of a transaction within a service varies. In its purest form, each step of a saga actually updates a single DDD aggregate. Which is quite interesting. And then at the same time, that a local transaction will emit an event or a message to a message broker, which will then trigger the next local transaction in some other service. And there's an interesting issue about making both of those things, the database update and the message publishing, happen atomically. Because if you think about it, the traditional way of doing that with distributed would actually be to use a distributed transaction involving your JDBC database and your JMS message broker. But that's not what we want to use. So later on, I'll mention some alternative techniques. So, in the case of the CreateOrder Saga, it sort of would look something like this, right? Where a request comes into the order service to create or place an order, and that request is going to initiate the saga. And the first thing it will do is create an order. And then the second step of this saga is to reserve credit. The first step, by the way, created an order in a pending state saying, well, it's been created, but we're still in the process of verifying that this is a valid order. And the next step was to reserve the credit. There might be additional steps to reserve inventory, for example. And then the final step is, well, the credit was reserved, so the order can now be approved because we validated it. So that's the idea. So each of this, you need to do two things. Reserve credit, create the order. It's been broken down into a series of local transactions. So that's fairly simple. But there's some interesting issues around this. So one obvious point is, well, what about rollbacks? So in an ACID transaction, you can do arbitrary inserts, arbitrary updates, delete some rows. And then at some point, you can decide, we're going to violate a business rule if we proceed any further, right? Which in this case would be, well, we've exceeded the available credit. Now, with an ACID transaction, that's actually quite simple to fix. You simply roll it back. And it's happened automatically. But with a saga, it's much more complicated because each of the steps that preceded the one that's failing have actually committed their results, right? So they've actually performed updates to the database, which can't be automatically undone. So you have to use what are known as compensating transactions, where, well, if I've updated data in services A, B, and C, and then in D there's a failure, I actually have to go back and explicitly undo what I did. which in some cases is trivial. Like, for instance, if you've credited the bank account, you just debit it to undo it. In other cases, it becomes much more interesting to actually figure out what to undo. And I'll talk about those challenges in a little bit. But at least conceptually, the model is this, where a saga is a series of steps, T1, T2, T3, and so on, and each one of those steps has a corresponding compensating transaction, C1, C2, C3, and so on, which undoes what the corresponding T transaction does. So let's imagine that T2 fails. So we've executed T1, that's updated the database. Then we're going to execute T2. We now have to execute C1 to undo what T1 did. So the sequence becomes T1, T2, C1. So that becomes the model. So you have to explicitly code this. You can think of a saga as, at some level, a state machine that is keeping track of what it has done, so that if there is a failure, you can explicitly go back and undo the changes that you've made so far. It sounds complicated, but at least say in this case, right, where you're reserving credit, it's not that hard, right? So if you cannot reserve credit, then the compensating transaction, the C1 in this case, is simply to mark the order as having been rejected due to insufficient credit. I guess we could delete it, but that would be weird because the customer had placed it, and so we wouldn't really want it to just evaporate. So that's the idea. You have to write these compensating transactions with this sort of state machine in order to sequence the steps. And it turns out there's a couple of different ways to do that. Two sort of coordination mechanisms, which is what I want to talk about next. So it's sort of basically with every step, what we've done is, we've done TI, which either succeeded or failed. So we now have to figure out what the next step to do. So if it's, successful, we have to execute T sub I plus 1, or maybe there's branching, and so there's some decision sort of based logic to do. If there's a failure, well, we need to start executing the series of compensating transactions. And if each one of those has failed, if we've executed, CI, we have to then execute C sub I minus 1, and so on until we've kind of undone all of the transactions. So, it sounds sort of complicated, but it isn't necessarily. But there's basically two models for this. So one is kind of choreography. So this is sort of kind of business process workflow type terminology. So one approach is choreography, where the decision-making is not sort of explicitly written down anywhere. It's just sort of diffused throughout the system. And then there's orchestration, where there's an object that is responsible for deciding what to do next. And there's interesting trade-offs with each one. So if we look at how choreography works, it's just the participants in a saga just emit events that then these events get received by other participants, which perform their own steps and emit more events. And so we've just got events flying back and forth. And because of the way we've implemented the event handlers, the right thing just happens. And it works really well in simple cases. So in the case of placing an order, it would sort of work like this, right? So request comes in to create an order. The order service creates an order and publishes an order created event, which gets, say, it's an event that's published to a message channel. Customer service is subscribing to that message channel and will reserve credit or attempt to reserve credit. It will then publish an event indicating the outcome of that credit reservation. Either credit was reserved or the credit limit was exceeded. and that goes back into, well, gets published to the customer event channel, which the order service is subscribed to, and then it will just either approve or reject that order. So in this case, it's pretty simple. These two services are implementing this Saga just by emitting events and subscribing to the appropriate events. And if you're familiar with event sourcing, this kind of choreography-based coordination is fairly straightforward. It just kind of comes naturally just from using event sourcing. But you can implement this quite easily just by explicitly publishing events. So in this example, this is an order service from one of the examples I have online, where it's Spring Boot, it's JPA for persistence, and there's an explicit domain event. There's an API, a domain event publisher class that just lets you publish domain events. And this is just a wrapper on top of the message broker client. And so the CreateOrder method in this example, creates an order, saves it in the database, and then it publishes an order created event. So just sort of very straightforward, explicit publishing events. And then the customer service has an event handler that is subscribing to the events that get published to the order events message channel. And so when an order created event occurs, this method, order created event handler, gets invoked, which attempts to reserve credit. And if it succeeds, it will then, based on the outcome, it will either call the domain event publisher to publish a credit reserved event, or a credit limit failed event. So really straightforward programming model. And in the simple cases, it actually works quite well. Especially if you're using event sourcing. And, with this model, the participants are just sort of loosely coupled. They're just subscribing to events, processing them, emitting more events. But there's some interesting issues with this. So in this example, the customer service has to know about all of the order events that imply a change to the available credit. So in this example, it knew that, well, when it sees an order created event, it has to reserve credit. But you can imagine that when the order has been, paid, it has to release that credit because we've got the customer's money. Likewise, if the order had been canceled, you've got to release the credit as well, and sort of so on and so forth. So basically, the customer service, even though its primary responsibility is dealing with customers, it now has to know all this stuff that's going on in the order service, which is just sort of doesn't seem quite right, even though you can make it work. Also, there are times when in some sagas where events just don't seem the right way to kind of cause things to happen. You end up with kind of wanting to publish I've requested that you do this for me event, which is really, really weird, right? So it sort of works well in a lot of cases, and I'd recommend using it. But there are just sort of these kind of issues that you can encounter which can cause problems. So another model is the orchestration-based approach, where there is an orchestrator, an explicit object, which is actually like a persistent domain object, that is telling the participants what to do. So instead of, for instance, the customer service having to understand the meaning of all these different order events, the Saga orchestrator is telling it, reserve credit, release credit, So in other words, the customer service is just exposing an API for reserving credit and releasing credit that these various sagas invoke. So it's kind of this different model. So yeah, so Saga, it's a Saga orchestrator, which I actually kind of abbreviate to the Saga, is this persistent object. So it sort of behaves like an aggregate in many ways that's basically implementing this state machine that's sort of tracking the state of the Saga and telling each of the participants what to do. So basically, when it's created, it will tell the first participant, go do this. And then the participant will send back a reply, which will cause the Saga orchestrator to be loaded from the database and told, well, here's the reply. And so that will then trigger a transition in the state machine. And the action will be to send a command to another participant, telling it what to do. And this state machine is dealing with sequencing the TIs, and then if an error occurs at any point, it's then responsible for sequencing the CIs, the compensating transactions. So it's sort of just an explicit representation of what needs to be done in this case, the CreateOrder Saga, or in general, it could be the Cancel Saga or the Revise Order Saga, and so on. So the way it would work with creating an order is like this. So, the same participants, but kind of the collaboration pattern is different. So first thing that happens is the order service actually explicitly creates an order. This could be done in the Saga, but sometimes it's useful to do it before creating the Saga. In a sense, this is step 0 of the Saga. Then the order service creates the Saga object. So think of it as another JPA or JDBC persisted entity. And then the first thing the CreateOrder Saga does is tell the customer service to reserve credit. It's invoking an API. In a little while, I'll explain that even though it looks like a REST call, for instance, or an RPC call, it's actually done via messaging in order to sort of give you guarantees around things completing. Customer service will then handle that request and then reply with the outcome. Credit was reserved. Credit limit exceeded. The CreateOrder Saga gets that reply and then approves the order. So similar sequence of actions, it's just that the pattern of collaboration between the two services is now quite different. Customer service no longer has to know about all of the life cycle events of the order service. It's simply just reserving credit or releasing credit. So that's kind of the big idea. Now, in terms of code, there's sort of a whole bunch of details on here that I don't want to go into, but you can see that this is this framework that I worked on. There's a simple DSL for defining the various steps of the Saga and then what actions to perform at each step. So this is a really simple Saga. There's only 2 things, right, that really get done. Well, the order's created, well, that's already happened, but the compensating action for it would be to reject the order. There's the invoke participant that says reserve credit, and then there's the invoke participant's final step that says approve. And each step is basically figuring out what command message to send to which participant. So this is basically sending a reserve credit command message to the customer service. So that's kind of what the Saga definition looks like. So it's basically a mini DSL for describing the workflow, kind of the sequence of steps for this Saga. And then in the customer service, it's basically responding to messages, command messages that it's receiving over a message broker. But this is all sort of abstracted away by just defining a command handler kind of for a particular type of message. And then what it's doing is just trying to reserve credit for the specified customer. Based on the outcome of doing that, it's sending back either a sort of success reply or a failure reply. So, if it succeeded, it sends back a success message saying, hey, the credit was reserved. Otherwise, it's sending back a failure message saying, I couldn't reserve credit because the credit limit had been exceeded. So that's the step. So anyway, both of these examples are online. So this particular one is sort of using this eventuate tram, whereas the eventuate tram Sagas examples, customers and orders. There's actually like 3 different versions of customers and orders online. One is implemented using choreography and JPA. Another one is implemented using choreography and event sourcing. And then this third one is using orchestration and JPA. So go take a look at that. Oh yeah, and as I mentioned, the participants here are all communicating using asynchronous messaging, which is super interesting because, these days it's kind of, you think of microservices, you think about REST, right? It's REST this, REST that, or maybe gRPC. But it turns out that I think once we start building more and more systems or business applications using the microservice architecture, you'll find that a lot of the communication will actually be done asynchronously. And there's some interesting concerns like, well, how do I publish a message as part of a database transaction without using two-phase commit? And then so the framework that I work on kind of deals with this. But the general idea is that these commands and the replies are actually being sent as messages rather than sort of RPC or REST. So when the CreateOrder Saga requests the customer service to reserve credit, it's actually sending a reserve credit command message to the customer request channel. So the customer service is listening on this channel for command messages, and then it's reserving credit. And then the reply message is being published to the channel every command message has a reply to header that says what channel to send the reply to. And that's actually a channel that the Saga is listening to for replies from the Saga participants. So there's just a bunch of messages going back and forth. And kind of like it just keeps going in this whole Saga. The actual, if the credit was successfully reserved, the Saga then has to approve the order. And that's actually done by sending a message via a channel. It's kind of like the service is sending a message to itself. Anyway, there's a whole bunch of lines and boxes, things are bouncing back and forth. But that's kind of the sort of the way the system works. And the reason for this, it really just gives you guarantees that, when you request an action to be done, this will guarantee that it will be done. The message broker is giving, the guarantee of at least once delivery. So even if the participant is not available to immediately process that request, it will eventually when it comes back up. And likewise, when it sends back a reply, in this case, if the order service is not available to handle the reply immediately, it will eventually when it comes back up. So sort of using messaging just guarantees that things will happen. And that's really important. REST and gRPC, they give you temporal coupling, which impacts availability, and that sort of basically doesn't give you the guarantees that you need. So anyway, that's orchestration. So kind of the nice thing about orchestration is that the definition of the Saga, the steps, the sort of the state machine that you're implementing, is defined in one place in this Saga orchestrator class, so it's a lot easier to understand. Unlike with choreography, where it's not written down anywhere, it's just implied by the behavior of the participant. It also means that so like the customer service, it doesn't have to know about order lifecycle events anymore. It's just exposing an API for managing available credit, and kind of gets rid of these cyclic dependencies as well. There is a risk that the Sagas kind of have lots and lots of logic, and the participants aren't that smart. But the solution is just don't do that, right? Just make sure that your Sagas implement kind of sequencing and coordination, and any real business logic just resides in the participants. Anyhow, so that's coordination. And you've got your pick. You can use choreography for simple cases, and then orchestration for the more elaborate cases. The key thing is everyone's communicating, in both cases, asynchronously, either by using events or by using command and reply messages. So the final topic I want to talk about is sort of the most interesting one in a way. Namely, well, like ACID transactions give you great guarantees, right? Like, namely, you have, the I in ACID means isolation. So these transactions just sort of execute kind of the transaction management system creates the illusion that every transaction is being executed in isolation, with the end result being that the concurrent execution of multiple transactions, the outcome of that is as if they were executed one after the other, right? I mean, that's the point of isolation. So you have this concept of serializability. Though we tend, for very practical reasons, to relax that constraint, right? Like, I think it's relatively rare to use the serializable isolation level in your database systems, right? You kind of run with a more relaxed isolation model in order to have better performance. But anyway, ACID transactions give you isolation. Now, what's interesting about Sagas, on the other hand, is that the execution of them can be interleaved, right? So, this CreateOrder Saga, there's the creating the order step, and then there's the reserving credit step. But those are two distinct transactions. So there's always the possibility that in between, someone could execute another transaction that tries to update that order. Like cancel it, for instance. And then it's like, well, what the heck does that mean, right? What does it mean to cancel an order that is actually in the middle of being sort of created? And there's, it's kind of an interesting issue. And I sort of, there are ways to deal with it. So one thing is, well, you could just not allow it, right? You could, say the user hits a cancel button and that order is still in the process of being validated. You could just sort of, say sorry, right? You can't cancel this order. We're still trying to figure out whether we can accept or reject it, right? But that's kind of unsatisfying, bad user experience. So let's imagine that you wanted to do this. Well, you could just go ahead and cancel it, but then what the heck does that mean? Because the CreateOrder Saga is in the process of sort of finalizing its creation. It might actually even go off and authorize the consumer's credit card, right? And if we canceled it, and then at the same time we're charging the credit card, that's not quite right either. So, so there's this notion where you could try and interrupt the cancel order saga by changing the state of the order and hoping that the CreateOrder Saga notices. But that's a little complicated. Or the cancel order saga could wait until the CreateOrder Saga completes, which actually sounds kind of like a lock, right? If I'm saying wait until CreateOrder, until the order has either been approved or rejected, that is equivalent to basically locking the order. So this was sort of the things I was thinking about, and it was sort of unsatisfactory in a way. I mean, these are solutions that you can actually make them work, but it was sort of like, this is compared with like like with ACID transactions that sort of have academic rigor. People write, kind of put a lot of thought into it. It was a little unsatisfying to use what I thought were sort of random mechanisms to deal with this problem. But then it turns out that some academics had been thinking about this. So there was this interesting paper, great title, Semantic Acid Properties, blah, blah, blah. But what it proposes is this notion of using countermeasures to deal with the problems that I just described, which are anomalies. Sadly, the paper is like, you actually have to buy it. It was written quite a long time ago. But it's actually a very useful source of information. It has this great kind of conceptual framework for thinking about sagas. So in its model, sagas are actually ACD. So they're atomic because the saga mechanism guarantees that all of the TIs will be executed or the compensations will be executed, right? So, atomicity is sort of, in this definition, is, well, it either all happens or it doesn't. Well, sagas give you that. They're also consistent, just sort of in an eventual sense. So each service is responsible for the consistency of the data that it owns, and referential integrity across services is handled by kind of the application logic. And it's also durable. When a local transaction commits, it's committed, it's durable. But there's this lack of right? There's a lack of isolation, which leads to anomalies. So if you go back and read sort of classic database literature like the transaction book by Gray, they talk about isolation and anomalies. So that's kind of the problem that you run into. And there's like, three main anomalies you can encounter. So one is lost updates. So in this scenario, the first step of Saga 1 creates an order. Some other transaction then comes in and updates it. In this case, cancels it. And then the final step of the CreateOrder Saga approves it. Even though it's been canceled, it just overwrote the changes that were done by the cancel order. You never have to think about that in an ACID transaction. This just can't happen because the data is rows are locked, basically, or the equivalent. But in this scenario, unless you explicitly code for it, it can happen. Another one which is very interesting is this concept of a dirty read, right? So imagine that somehow you're manipulating the credit of a customer. So you reserve the credit as the first step of a saga. Another transaction comes in and reads that credit and makes a decision based on that value, like, oh, can I place another order for this customer? Yes, there's sufficient credit. And then the first saga basically executes a compensating transaction that undoes the change that it just made. So that the second transaction actually made a decision based on data that on the current available credit that has just been compensated. So that in database terminology is a dirty read. Once again, that can't happen in an ACID model because you can only ever see committed changes. And that has consequences. In this case, it meant that an order couldn't be placed even though it should have, which is maybe okay, but if this was the other way around, where it was increasing the available credit and then compensating was reducing it again, then you would end up with an order being created that should not have been approved. So that's kind of an interesting little problem. And then another problem is that the Saga could do 2 reads, and then in between, someone else can update the data. So it's sort of get these fuzzy, non-repeatable writes. Once again, can't happen with ACID transactions. So that's the idea, and this paper proposed a series of countermeasures to deal with this problem. And it's really all about reducing the impact of these anomalies, as opposed to, it's sort of like this lack of isolation is something you have to live with, but you just try and reduce it in a way that it doesn't have a significant impact on the business. So one thing you can do, the other thing that this paper introduced was kind of giving Sagas a structure. So in their model, the first few steps of a Saga are these compensating transactions, or are these compensatable transactions. So in other words, they are steps that have a corresponding compensating transaction. And then there's what's known as a pivot transaction, which is sort of like this go-no-go step, where if this succeeds, the rest of the Saga is guaranteed to succeed, whereas if there's a failure, then you have to execute the compensating transactions. So if you think about banking, right, you can always credit an account, in a simplistic model. But that's something that can always be done, but then a sort of a pivot transaction would be something like debiting the account, in the sense that might not succeed because the balance can't go negative. So, they've got credit and debit have slightly different properties. And then after the pivot transaction are a series of transactions that are just guaranteed to succeed. So the debit would be a pivot transaction, and the credit account would be a retriable transaction. They just can't fail, so there's no need to have any compensating transactions. So in other words, if you put stuff after the pivot transaction, it ain't going to fail. It's always, which is kind of important. So that's the idea. So there's a whole series of countermeasures. So one of them is basically, is to reintroduce long-term locks. So in other words, you have some transaction, a compensatable transaction will actually, like in this case, lock the order by saying this order is in the pending state, and then eventually when the order is approved, you've got a retriable transaction that unlocks the order by changing its state to approved. So anyone who comes in and reads that order will know, this order is pending, and either I can't do anything with it, or I'm going to treat it very carefully. So we're reintroducing these long-lived locks, which might require a locking mechanism. Another strategy is to define your transactions to be commutative. So it doesn't matter what order they're done in. And if you think about, debit and credit are 2 operations that can be done in either order, and then, you actually have this commutative property. So that's a useful mechanism that simplifies your logic. Another mechanism is to actually change the sequence of the local transactions in the Saga, so that the steps that introduce business risk are done last. or to be more precise, done as retriable transactions which won't be compensated. So rather than increasing the available credit at the beginning, where you run the risk of having to compensate it and reduce it again, which creates the risk of a dirty read, you put the increase of the available credit at the end. So there's no chance of a dirty read. A way of dealing with fuzzy reads is basically to use a variant of the offline optimistic lock pattern and reread the data again later on in the saga, and if it's changed, go, it's sort of the data's changed underneath me, I'm going to restart the whole sequence of steps. So kind of like executing the compensating transactions and redoing. And then another mechanism is to basically, what they call it a version file, that's kind of a weird name, but it's like to record the sequence of operations on an object, like, oh, it's a payment, so it's been authorized or it's been reversed. So if those operations occur out of order, you can look at it and go, oh, well, you said reverse this credit, and now you're telling me to authorize it, and the net result is the same as if I had authorized it and reversed it. So you just kind of reorder the sequence of operations. And then the final one, which is really interesting, I don't know how practical this, but they talk about it in this paper, is based on the specific scenario, like the dollar amount of that's say being transferred, to use to then select the appropriate way of maintaining data consistency. So like actually have the ability to implement distributed transactions, but only do it when you're transferring $1 billion, because you want to minimize the risks to the business, and the availability of that transaction doesn't matter. Intriguing idea. As I said, I'm not sure how well it would work in practice, but something to consider. Anyway, I am like out of time, so that's pretty much my talk, fortunately. So sort of in summary, right, like microservices are enabling, continuous delivery of complex applications. You've got a database per service to ensure loose coupling. And so you need to use sagas, either choreography-based sagas or orchestration-based sagas, to maintain data consistency between your services. And then you have to use some combination of countermeasures to reduce the impact of anomalies because of the lack of isolation. So that's my talk. Hope you found it useful. Thank you for listening. And please check out my book. Thank you.